Math 30-1. Lesson 2 is about measuring angles and radians. In our previous work in Math 10 and Math 20, and even our review in Math 30, we've always dealt with angular measure in degrees, and that's great. However, there are other ways of measuring angles. And in calculus, the way we measure angles is radian measure. So this is an exploration about what is radian measure and how would we measure an angle in radians. So I would like you to complete this exploration, play with it, and build an understanding for radian measure. All right, now that you're back, let's see if I've done okay. So I've got my ruler out, and according to my measurements, I can see that this measurement, if I move my ruler just a little bit back and forth, it seems that this is exactly 5.5 centimeters according to my ruler. So if that's 5.5 centimeters, I go and I cut a piece of string. I take my piece of string and I cut it to 5.5 centimeters. And I did. I now place, so I take that piece of string that I cut and I place it on the circumference. And I'm going to start by going this way. So I took my string and I place it on the circumference, and I'm just doing that right now. You can't see me, but I am. And as I place that string on circumference, I'm going to put a mark. And I look, oops, well, now you can kind of see what I'm doing. And I put that mark at the place on the circumference, and try and read the numbers, and I end up with it being right there. And I put the point Q, mark the letter Q at the circumference, and I joined that string. So there's my string, and it measured right to their point Q. I state the length of OQ. Well, I know that it's still 5.5 centimeters, and the length of that arc, is the same thing as 5. So an arc is a piece of a circle. About how many times will that string equal to the length of the radius fit around the circle? So now you just keep repeating that process. So we'll call that Q1. That was the first time that happened. So I'm just going to continue going around the circle, and you do the same thing with your string, or you already have, right? And as I go around, I see that. So there is a little point, and I'll call that Q2. And I do it again. Take my string and lay it around the circle, and there it is again. Whoops. There's Q3. How many times will it go around? Well, I'll keep going. And there it is. Q4. Will it go again? Well, let's see. So I move it again. And that was Q. That's right on top of my ruler. Q5. And I go again. And it goes right to about there, Q6. So, what did I just find out? Well, it goes around 6 times and a little bit. How much is that little bit? Well, let's continue on. In the diagram, oops, I forgot to do this. Determine the circumference of the circle to an exact measure. Give the answer as an exact value in terms of pi. Well, the radius was 5.5 centimeters. That was supposed to be up here. I forgot to do B, and that means that I know the circumference of a circle. The circumference of a circle is equal to 2 pi r, and so therefore I know that this is 2 pi times my radius, which is 5.5. So now when I think back to this part down here, why does it go 6 times and a little bit? Well, when we think back to this part up here, where does that little bit come from? Well, when you think about what 2 pi is, now that's the exact value up here. This was exact, but when you think about what 2 pi is times that 5.5 centimeters, well, 2 pi is really 2 times 3.14, so it makes perfect sense. How many little 5.5 centimeter strings are there? Well, there's 6.28 strings or radiuses that it takes as you go around the circle, right? That's why there's 6 and a little bit. So in general, the measure of POQ, when we think back to our diagram, POQ, that very first angle, POQ is a measure of 1 radian. And why is that? Because the measure around the outside, the arc length of that angle is equal to 1 radian. In that diagram, the measure of POQ is defined as 1 radian. In general, a radian measure of a circle is the ratio that compares the length of an arc to the radius of the circle. The measure of an angle in radians is equal to arc length divided by radius. Or on your formula sheet, they'll have a formula that says theta in radians is equal to arc length divided by A over R. In diagram 1, the measure of AOB is given by the ratio, and we use that definition to estimate radian measure. As indicated, 1 radian is the measure of an angle formed by rotating the radius through an arc equal to the length of the radius. When it says estimate the degree measure, well, we already talked about, well, it takes about 6 radians to go around a circle. So when you look at it, it must be approximately equal to about 60 degrees. A little bit more than 60 degrees, but it's about 60 degrees in terms of degree measure. The next part, and it's going to be important for us to be able to convert between degrees and radians, and also the other way as well. So first off, since an angle can be measured in degrees or radians, we have to be able to convert. 1 complete rotation is obviously 360 degrees. The arc length for 1 complete rotation is 2 pi r, which is the circumference. Well, the ratio of arc length to radius for a full circle is 2 pi r, so that means that 360 degrees must be equal to 2 pi. So now we get this conversion factor that 1/2 rotation must be 180 degrees. The arc length for 1/2 rotation is pi r, so if the ratio between pi r and radius, the angle for half rotation is pi. Therefore, pi is equal to 180 degrees. Well, that makes sense. 2 pi around a whole circle, pi around half a circle. So, if you want to know what 1 radian is, that's what these conversions are. Somebody said to you, well, what's 1 radian? Well, we can simply say, well, pi radians is equal to 180. So if I divide both sides by pi, then 1 radian is really just equal to 180 over pi degrees. What about 180 degrees? Well, if you want to change 180 degrees to just 1 degree, you would divide both sides by 180, and if you did that, 1 degree would be equal to pi over 180 radians. So in order to convert from radians to degrees, you would multiply by 180 over pi. In order to convert from degrees to radians, you'd multiply by pi over 180. In mathematics, if we see the symbol degrees, it means we're dealing with degrees. If there's no unit, so this is just a convention, then the abbreviation is radian. So if you don't see an angle of degrees, it's assumed that it's radians. So for example, you might think that automatically, because 90 is one of our favorite angles, that they're talking about 90 degrees, but they are not. This is talking about radians. And so you need to be careful when you see an angle, is it talking about degrees or radians from now on? It doesn't have to necessarily have pi in it, all right? And this little box is kind of memorizing how to convert, but another way to just think about it is in terms of unit conversions. And so, for example, if we know that this conversion factor is pi over 180 or 180 over pi. And if you put units on these things, which they don't have right now, but if you do put units, pi is usually considered radians and 180 is usually considered degrees. And so if we have units here, when somebody says, hey, I've got an angle of 60 degrees, can you please convert that? So you can memorize this chart, or you can just say, well, I really want to blow up these degrees. So if I'm going to convert that to radians, I have to multiply by pi over 180. And the reason is that you do that is because this is degrees, and you really want degrees, kind of like physics, you really want the degrees to cancel each other out and be left with the units of radians. So what is 60 degrees when it's converted to radians? Well, the degrees canceled out, and you're left with 60 pi over 180. The 60 cancels with 180 and you're left with 3. So in simplest terms, that's equal to pi over 3, and obviously that's now in radians. So you don't have to memorize this chart, but you can. Now we're going to get into using this and converting back and forth between degrees. Okay. So on the next page, use these conversion factors to convert. So for example, and we want these as exact values. We don't want these as decimals, right? So there's difference. And so you wanted it in terms of pi. We're not going to put it as a decimal. Okay, so for the first one, like I said to you before, if I want to change 270 to radians, I'll put pi over 180 because I need that. Now that degree symbol's in the wrong place, because I want to blow up the degrees, right? So it's 270 degrees, the degrees will blow up, and you end up with 3 pi over 2. If you have 315, you multiply by pi over 180, and if you're wondering what's happening there, there's a common factor of 45, and 45 goes into 315 7 times, and 45 goes into 180 4 times. That's why you end up with 7 pi over 4 radians, right? Now, sometimes they want these degrees into radians, but the nearest tenth. So you're still going to have that same conversion factor, but now you're not going to. Leave it with pi. You're going to round it, and I should put approximately, because it's not equal to. That is approximately equal to 1.2. So 70 degrees, if you convert it, would be 7 over 18 pi as an exact value, but then that would be equal to 1.2 if you put it to one decimal. If you multiplied 205 by pi over 180 as an exact value, I'm just going to put it over on the side here, as an exact value for reduce that fraction, 205 degrees would be 41 over 36 pi, 41 pi over 36 as an exact value, but they wanted us to write it as a decimal, so it's approximately equal to 3.6. If you want to convert those radians to degrees, well, now you go the other way, and notice that if I just think about units, you want to blow up the radians with radians and leave behind the degrees. So that's why we're multiplying by 180 over pi instead of by pi over 180. And when you simplify that, we end up with 45 degrees. And when you multiply minus 7 pi over 3 by 180 over pi, I'm not showing all my work, but the pi's cancel out. And if you reduce this fraction, 3 goes into 180 60 times, and 60 times minus 7 is minus 420 degrees. Okay, so that's what's going on. And that's as an exact value. Sometimes radians don't come with pi in them, right? Sometimes they actually just are whole numbers, and sometimes they're decimals. So these radians, they're exact, but they're exact decimals. So how do you convert 1.57 as into an angle in degrees in nearest tenth? Well, you still multiply by 180 over pi, and when you do that, you get approximately, okay, we don't want to say exactly, we get approximately 90 degrees. And minus 1.4, well, you're still going to multiply by that 180 over pi conversion, because you want to blow up the radians and leave behind, and you end up with about approximately approximately minus 80.2 degrees, okay? We still have coterminal angles just like we had with degrees, right? And just to refresh your memory, what are coterminal angles? Well, every angle that we have in degrees, and remember, so let's say I start with a 121 degree angle. That's my angle of theta. Well, there is an infinite number of coterminal angles. And if I wanted to add 360 to that, if I add 360, that would be 481 degrees. If I subtract 360 from that, I would get minus 239, minus 239 degrees. So those are just two of the coterminal angles that are there. But there's an infinite number as well, and we can write that by writing the principal angle, 121 degrees, plus n times 360 degrees, where n is an element of interest. Those are all the family of coterminal angles that, that have a principal angle, 121, right? So coterminal angles and radians are separated by 2 pi degrees. And like we talked about before, principal angle is between 0 and 360, or in this case, 0 and 2 pi. The reference angle is formed between the terminal arm on the rotation of angle x, and just like it was before. So in quadrant 1, we have the reference angle, right? In quadrant 2, so this is just speaking to what's the relationship between a reference angle and the actual angle of theta. So in quadrant 1, if you got a reference angle, then what's the actual angle of rotation? Well, it's just the reference angle. But if you have an angle in quadrant 2, well, then that would be 180 degrees minus the reference angle. And it would be the same thing in radians, except for it'd be pi minus the reference angle. And if you went to quadrant 3, well, obviously in degrees it'd be 180 plus the reference angle, but in radians it's going to be pi plus the reference angle. And lastly, in quadrant 4, if you went with the reference angle in quadrant 4, you'd take 360 minus that 60 degrees, and you would have 2 pi minus the reference angle. So when you think about what these angles would be, if we use our 60 as an example, then this would be 60, this would be 120, this would be 240, and this would be, this is going to end up being 300 degrees. All right. Now you're going to do the same thing with actual values for radians, right? And if you were to, may not like working with fractions, but 60 degrees is actually pi over 3. And so if you had 1 pi minus pi over 3, a little bit tougher to do in your head, but pi minus pi over 3 is really just 2/3, because 3/3 minus 1/3 is 2/3, and pi plus 1/3 is equal to 4/3. And 306 degrees, which is 2 pi, minus 1/3, well, 6/3 minus 1/3 is 5/3. It might seem a little more complicated in degrees, but it's actually not. You'll get comfortable with it. You just have to get used to that. All right? Carry on. Okay, so we have to get comfortable with drawing these 60 degrees and 120 and so on. We've got comfortable with degrees, but let's do radians. So remember, I'm going to start by doing this. 0, this is 1 whole pi. This right here is also coming around to 2 pi, so 0, 360. This right here would be pi over 2, and this right here would be 1.5 pi or 3 pi over 2. So you got to get comfortable with rational numbers. So where is 3/4? Well, 3/4 is more than a half, so it's definitely in this quadrant right here. That's where 3 pi over 4 belongs. So I drew the angle. Now I need to state the principal angle. Well, part 2, the principal angle is clearly 3 pi over 4. Question number 3 says, well, determine one positive and one negative coterminal angle. Well, it's almost easier because what you have to do with 3 pi over 4 is add 2 pi. Now, here's what I'm going to do. 2 pi is really, in terms of 8 over 4. So I changed it to 8/4, right? 8 divided by 4 is 2. So if you add 8 quarters, then really what you have is 11 over 4. Man, that was easy. And if I subtract 8 over 4, then I would have minus 5 over 4, right? So adding or subtracting, and I could do a gazillion of these. If I added another 8 pi over 4, then I'd be at 19 pi over 4. And if I subtract another, do negative angles, another 8 pi over 4, I'd be minus 8 and 5 is 13 pi over 4. So it's really easy to come up with coterminal angles. Write an expression for all the coterminal angles. Well, that's easy. That would be 3 pi over 4. This is part 4. 3 pi over 4 plus n 2 pi, where n is an element of integers. All right. And I do that with minus pi over 3. Well, minus pi over 3 would be in quadrant 4. There's minus pi over 3. Why do I know that? Because this is 0. This would also be 2 pi. And if you go the other direction, this would be minus pi over 2. And this would be minus pi. This would be minus 3 pi over 2 if you went the other way. So clearly minus pi over 3 is there. What's the principal angle? Ooh, the principal angle, we have to be careful with that. The principal angle needs to go this way. Tick, 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 tick. So the principal angle is actually, if I add 2 pi over 3, if I add 2 pi to get myself back around, the principal angle is actually 5 pi over 3. And if you wonder how I got that, well, one way is just to take 2 pi over 3 and add 2 pi, which is really 6 pi over 3. That's how I got that, right? You're getting rid of the negative rotation. So in part 3, if I need to add some extra, or if I need to find out some other coterminal angles, well, it's really easy because I just take that principal angle and I subtract or add 6 pi over 3. So I could have 11 pi over 3, or I could add 17 pi over 3, or 23 pi over 3. Any of those, because I just keep adding 6 over 3. Or I could subtract them and I'd have minus 7 pi over 3, or minus another 6 is minus 13 pi over 3, or minus 19 pi over 3. It's easy to come up with coterminal angles. And lastly, the fourth thing is, what are all the family? Well, I take the principal angle, which is 5 pi over 3, plus n 2 pi, where n is an element of integers. Determine the reference angle for each of the following. Again, it's probably best if you just draw it, right? Draw each of these angles and find out their reference angle, just like we had in that previous chart. So when you have 4 pi over 3, where does that belong? Where does minus 5 pi over 4 belong? And where does 23 pi over 6 belong, right? Well, 4 pi over 3 is actually 1/3 more than pi. So it's going to be in this quadrant right here. There's 4 pi over 3. And if this is pi, then it's really just 1/3 more than pi, right? Think about it. Pi is really 3 over 3. So the reference angle is going to be pi over 3. What about minus 5 pi over 4? Ooh, that one's kind of cool. Okay, that's definitely going to be in quadrant 2. How come? Because this would be minus pi, and minus 5 pi over 4 would be 1/4 more than minus pi, right? So the reference angle for this one is equal to pi over 4. 23 pi over 6, that's a lot. 23 pi over 6. 23 pi over 6 minus 2 pi, because that's definitely got some extra rotation, ends up being equal to 11 pi over 6, because you subtract 12/6 off there. Now 11 pi over 6 is all the way around, but it doesn't quite make it to 2 pi. In fact, because 2 pi is 12/6, it's 1/6 less than 2 pi. So it's in this quadrant, and that reference angle for this one is equal to pi over 6 in quadrant 4. Okay, I'm going to pause right now because that's enough for this, and I'm going to make a different for the actual arc length assignment. So if you wanted to begin the assignment or come to class, and we'll finish this up in another segment.